Welcome Algebra 2. This is 11.5, Probability Models. The essential question is, how can you use probability models to analyze situations and make fair decisions? Let's begin. So probabilities help you determine if something is fair. So we're actually using these in real life examples, and this is what you can use in your day-to-day lives. So what does fair mean when I talk about fair? You're an equal chance for all participants. So not fair like it helps you out, fair like it helps everyone out equally. So I can use math to prove if something is fair or not fair. So what if I rolled a six-sided die, and we have two players? Player A wins if it rolls odd, and player B wins if it rolls even. Well, is this fair? Yeah, because it's going to roll odd when you get a 1, 2, 3, or 5, and even when you get a 2, 4, or 6. So player A wins 3/6 of the time, so 1/2 of the time, and player B wins 3/6 of the time, which is 1/2 the time. An example of not being fair, we said A wins if the roll is greater than 2, and B wins if the roll is equal to 1 or 2. That's not fair, because player A wins when you get a roll of 3, 4, 5, or 6, which is 4 out of 6 chance, which is 2/3, and player B wins when you get a 2 out of 6 chance, which is only 1/3. So it gives an advantage to player A. Let's talk another scenario. So say you have a class of 25 students, and you want to choose 3 students at random to bring food for a class party. Any set of 3 students should have an equal chance of being chosen, to be fair. Which of the following strategies will result in a fair decision? If I'm looking at this, so what if I line the students up alphabetically, and each one has to flip a fair coin? So 50-50 chance heads or tails. The first 3 students to flip heads bring in food. Is this fair? No, it's not fair. Because what's going to happen is the people at the start of the alphabet are going to flip, and you know what? If you're only picking 3 students, chances are you're not even going to get to the end, because if it's a 50-50 shot, you'll usually finish by about the 6th person. So I'll say no. Usually get all 3 by the 6th person. So people at the later end of the alphabet, like with a Z, they'll never get picked because you're going to get 3 heads before you actually get to that person, most likely. Let's try this scenario. Each student draws a card from a well-shuffled 52 deck of cards. A teacher shuffles a second deck of cards, spreads them out, and draws cards one by one until he matches the cards of the 3 students. So everyone gets a card, a standard deck, and then teacher has another standard deck that's shuffled and picks out 3 random cards, or cards until they pick 3 students. Is this going to be fair? Yes. And as long as that deck is shuffled well, that the teacher picks from, and it's truly random, it's been shuffled sufficiently, then it's completely fair, because you're going to pull out cards and each card has an equal chance of getting picked, as long as the deck is shuffled well. So for an event to be random, there's no predetermined pattern. So like that deck of cards, if it's shuffled well, you can't predict the pattern. But sometimes we want to simulate this, and one way we can do this is through a random number table. So we use these for models. And how do you create these? So here's an example of one. How do you create that? You don't just start picking numbers randomly and start writing them down, because if you just pick them from your head, it's not truly random. You can use computer programs will have this. Any computer language will have some function to do this. You can roll if you don't have computers, you can roll dice. If you had a D10, a 10-sided die, and you just kept rolling that and give it a good roll every time, then you get a fair distribution. You could also pick numbers from a hat, so you put 10 numbers in there and they're all equally sized and weighted, and you just kept pulling it one at a time. That could be random as well, as long as it's well distributed and well shaken up. So let's use that random number table. Coach wants to select 3 of her 15 basketball players at random to lead warm-ups. Coach assigns each player a number from 0-1 to 15. So 0-1, 0-2, all the way down to 1-5. How can the coach use a random number table to fairly choose these players? So if you make this random number table, coach can, first step they could do this, they could choose a line of digits at random. So if you choose out of 4, you'd need some way to randomly pick a line here. So let's say the coach did something, 4-sided die, and picked number 2. So row number 2. And then what they could do is they could read the digits from the random number table in consecutive pairs until you get the number of 3 pairs. So if I'm reading this line right here, the first 2, 1, 4, well, there's player number 14. So that'd be the first pick. And I keep going, oh, player number 15. and then I keep going. And it's a 2-digit pair, so I can't just say, oh, I see number 8, player 8. No, it's 0, 8. So I keep going, and I don't see anything. I say, oh, wait, there's 0, 8. So that person gets picked. So the 3 numbers, and everyone is assigned a 2-digit number. Those are the 3 people I picked. This is one way to do this. Now, there's flaws in this system if the coach kept using the same random number table, because these were generated randomly, but if we use the same numbers again, we're still going to get the same 3 players. So there's got to be another way we can. So even though that's random, you can't always just use that same random table every time. A probability model. So sometimes we're going to use it to assign probabilities to outcomes of a chance process. And we're going to use it to simulate something. So here's an example of using a probability model. You go to a fast food restaurant and they give away toys. And you want to collect all 4 different toys. And let's say each toy has the same chance of getting picked. So that's a 1 out of 4 chance, 25% chance. About how many kids' meal would a parent expect to have to get all 4 toys? So we can simulate this with a probability model. And our probability model is this spinner thing here. So you make a circle spinner, and each section has 1/4 of the thing, so each section is 25%. And you spin it, and you give it a good spin every time. Everything will be perfectly fair. So what you could do is you could spin the spinner and keep track of your outcomes, like by a little table. And here's an example of that happening. So they simulated 1, 2, 3, 4 toys and put a tally mark, and they kept going till they at least put 1 tally in every toy. So this was one simulation. We went through this, and that's what we got. Now you can't just do the simulation once and say, oh, it's going to count all this numbers up. It's going to take 8 times. So this one took 8 tries to get all toys. Say, oh, 8's the answer. You can't, because different players could have a different amount of picks. One person might only take 4 picks. So here's repeating that simulation several times. So one person got 7, one person took 12, this person only took 5. So there can be a lot of differences here. So you want to repeat that until you get a good sample size. And now you want to find the average of all these samples. So when you have all these, some are going to be really low and high. You want to average them all. And since there's 25 and they all add up to 227, the average is 19 and 8 1/100ths. So on average, you'll need to buy about 9 kids' meals to order to get all 4 toys. So that's one way to use a probability model. Now, we can also use an existing probability model to analyze a decision. So this is a pharmaceutical company. They have a drug and they do a test, and they have the drug so they have a drug, and they had 160 volunteers. 80 are given the drug, and 80 are given a placebo, so a fake. After 2 weeks, the volunteers said, hey, I'm better or I'm not better. And here's the survey results. So looking at this, so these are those that received the fake, and the totals right here. What's the probability of a volunteer reported noticeable improvement in their symptoms given they received the test drug? So we can say the probability of improved given they received the drug. So you receive the drug's the top column, so it's going to be 67 improved out of the total 80. So that's that probability. Now what's the probability a volunteer received the placebo given that he did not report a noticeable improvement? So probability of given, geez, I'm lagging a lot. Probability of given the placebo given that they did not improve. So not improve. So not improve is this column, and placebo is going to be 56 out of the total, which is 69. So those probabilities. Now, this part's interesting. Pharmaceutical company decides to produce and distribute the good drug. The drug is marketed as an effective way to improve the symptoms of asthma. Based on the results of this test, did the company make a good decision? And explain. So I'm looking at the results. So I want to look at what percentage improved from those that had the drug and the placebo. So for the improved, the probability was 67 out of 80 improved. And then for the improved for the drug, so this was drug, I'm going to say improved of the placebo, that's going to be 24 out of 80. So does these results say that they made a good decision? I would say yes. Because if you're looking at those results, there was a lot more improvement when they actually used the drug rather than the placebo. All right, let's try some examples. Pause the video. All right. Two siblings try to decide who has to mow the lawn this weekend. They decide to race, and the winner does not have to mow the lawn. Is the result a fair decision? Explain this. I'm going to say no. A fair decision means each sibling has an equal chance to mow the lawn. You might say fair, they both get a race, but if one's older, I would say because age differences. If you're an older brother, teenage brother, and you have a little 8-year-old brother, you're probably going to be faster than them, and so you're going to win the race all the time till they get to your age, or you get really old or hurt. So that's not a fair way to decide the lawn mow. But if you're the older brother, you think it is. Try this one. All right, same. So the results of a drug test are here. Should the company produce and distribute the new drug? Basically, does it work? And so explain this. So I'm looking at my probabilities. So those that received the drug, those that received 23 out of 50 showed improvement. Those that received the placebo, 19 out of 50. Now, it's kind of up to your opinion. And should they distribute the drug? I'm going to say no. And the reason is I don't see much of an improvement. If it's only 4 extra people out of 50, so I'm going to say not much improvement. Now, you might say there's a little bit because, hey, 4 extra people said they're happy, but is that significant enough? And I think in later sections we're going to talk about if that's significant enough. You might say that you don't have enough information yet because you show some improvement, but maybe you just need to do new trials. But based off this data, I don't think there's enough to prove that this drug actually works, and you need more testing. That's it.